Ever wonder what a massive roller coaster and, say, a simple book on your desk have in common? Well, the answer is this fundamental force that shapes pretty much our entire world: energy. We're going to break down the basic principles, starting with something as simple as pushing a box, and build all the way up to the unshakable laws that govern the entire universe. All right, let's get into it. So, let's start right there with that little puzzle. What on earth connects the tiny act of lifting a book with the massive, heart-pounding drop of a roller coaster? The answer, like we said, is energy. And by the time we're done here, you'll see how this one concept is the invisible thread that ties literally everything together. So, our journey starts with a word you use every day, but in physics, it has a very, very specific meaning. That word is work. Let's dig into what it really means when a physicist says they're doing work. See, in physics, work isn't about how tired you get. It's all about a force actually causing something to move. You could push against a solid brick wall with all your might for an hour straight, muscles screaming, and you know how much work you've done? Zero. Absolutely none. Because the wall didn't budge. Tough crowd, physicists. The math behind it, though, is beautifully simple. The more force you apply, or the farther you make that object move, the more work you've done. It gives us this really clean formula you see here. Work is just force times distance. That's it. And just so we're all speaking the same language, scientists measure both work and energy in a unit called the joule. Just a handy little term to keep in your back pocket as we go. Okay, so you've done some work. You've pushed the box, but where did that energy you spent actually go? It doesn't just disappear, right? Nope, it gets stored, just waiting to be used. And that brings us to our next building block, potential energy. This is what we call gravitational potential energy. When you lift that book off the table, you're fighting against gravity. The work you did, the energy you used, is now saved up inside that book, purely because of its new height. It's just sitting there, ready to be released the second you let go. So how much energy is stored? Well, it all comes down to three things: the object's mass, how heavy it is, the pull of gravity, and, of course, its height. And since gravity is pretty much a constant for us here on Earth, the two things you can really play with are the mass and just how high you lift it. And this leads to a super simple, really powerful rule of thumb. If you lift a book twice as high, you've stored exactly twice as much potential energy. It's a perfect one-to-one relationship. So simple. But lifting things isn't the only way to store up the work you've done. What about changing an object's shape? This gets us to another really cool way to pack away potential energy, by stretching or squishing things. And this is called, you guessed it, elastic potential energy. Think about pulling back a rubber band, or drawing an archer's bow, or even just compressing a spring. When you do the work to change its shape, you're loading it with energy that's just bursting to be released. Now, the formula here is a little bit different. The energy you stored depends on K, which is basically how stiff the spring is, and X, how far you stretch it. But you've got to pay really close attention to that little 2 next to the X. That changes everything. That little 2 means the distance is squared. And because of that, the connection between how far you stretch and how much energy you store is not so simple anymore. So what do you think happens when you double the stretch? You get 4 times the energy. Not double, quadruple. That squared relationship means that every extra inch you pull back packs a way bigger punch. It's exactly why a fully drawn bow has so much more power than one that's only halfway there. So let's just put them side by side. You've got 2 main ways to store work. One is based on height, and it's a simple linear game: double the height, double the energy. The other is based on stretching, and it's an exponential game. Double the stretch, and you quadruple the energy. 2 different methods, same core idea. Okay, so far we've been talking about clean systems, moving a box, stretching a spring, but the real world is messy. There's friction, which creates heat, and to understand that, we need to zoom way, way out and look at the big picture, a universal law that runs everything from a steam engine to a star. And that law is the first law of thermodynamics. It's honestly one of the most fundamental rules of our reality. You can't create energy out of thin air, and you can't just make it disappear. All you can do is change its form. The potential energy of that roller coaster at the top of the hill turns into the energy of motion on the way down, and some of it turns into heat from the friction on the tracks. It's all just a conversion. When we're talking about engines, the law looks something like this.
The change in a system's internal energy is just the heat you put in minus the work the system does. It's like a perfectly balanced checkbook for energy. Nothing ever truly gets lost.
And this simple 3-step process is basically how every heat engine in the world works, whether it's the engine in your car or a giant power plant. Step 1, it sucks in heat. Step 2, it uses some of that heat to do something useful, like pushing a piston. And step 3, it has to dump the leftover heat somewhere else. But that third step, getting rid of the waste heat, is unbelievably important. It leads us to our final and maybe the most profound idea of all, the universal rule of efficiency. Or put another way, why nothing in this universe is ever perfect. Just look at this. When you burn fuel to make heat, you can't turn all of that heat into useful motion. It's just not possible. A huge chunk of it, always, is unavoidably lost. It has to be vented out into the environment as waste heat. And this isn't because we're bad at designing engines, it is a fundamental law of physics. The second law of thermodynamics flat out tells us you can never, ever build a 100% efficient engine. There's always going to be an energy tax that you have to pay in the form of waste heat. It's all part of the universe's unstoppable march toward disorder, a concept we call entropy. There's a famous quote that just sums this up perfectly. The first law says you can't win, meaning you can't get something from nothing. But the second law is even tougher. It says you can't even break even. You are always going to lose some of that useful energy. In the great cosmic casino, the house always, always wins. So that's where we'll end, from lifting a book to drawing a bow, all the way to the laws that run the cosmos. It's all about energy just changing its clothes. Which leaves us with one final thought to chew on. If all energy is just being converted, and we know some is always lost to disorder, what kind of energy transformation do you think is going to matter the most for our future?